Good afternoon, everyone. I hope you're doing great. Ali, good afternoon. Everyone, good afternoon. I hope you're doing great. Thank you. Ivan, Alvaro, Ruslan, and Binye. If you can hear me clearly and if you can see the screen, please type 1. Merci. Bravo. Thank you. The thing is, quickly, without any further delay, I'm going to go to the content, and hopefully you can help me to tell if everything is fine with the quiz, because the quiz is gonna get started right after the class. So later I have 2 hours back-to-back class after that teaching Python, but please let me know if there is any concern, any problem, anything about that quiz, just to have a kind of comfortable time zone. I extended the due to Thursday night, so you have enough time. And that is the @class code Lewis, DBIM. And I would be grateful, first, you're welcome, to tell me if it works. And if it is so, there is a chance that when I start teaching, I cannot check. Yeah, thank you very much, Luis. I cannot check the chats every second. So there is a chance that the other friends ask. Please share this with our friends if they ask. Thank you very much. So quickly to recap what we have talked about. We talked about the AI in general, and we said that the artificial intelligence, or AI, has the biggest zone, machine learning, and the learning concepts are subsidiaries of that. Not all the artificial intelligence are based on learning. Some of them are based on restrict rules. Actually, before 1990s, most of the attempts were based on restrict instructions, and they thought that if we have enough number of instructions, then computer can solve any issue. It was not the ultimate solution. We needed something that can learn by itself. So the concept of learning mostly happened after 1985, 1990s. We had artificial neural nets. The idea is 70 years old, but it had just only one hidden layer. So the real learning actually happened after 1985, mostly 2000, when the concept of machine learning was very much popular. And as Lucas correctly addressed, the initial AI, which was based on restrict rules, we called it symbolic AI. And machine learning started to flourishing. And after a while, after a decade, a subsidiary of machine learning, which was based on several layers, came to this world, and that was deep learning. In compared to deep learning, we could call those machine learning that had just a few or one layer shallow learning. That's something that you might see here and there. And we talked about the concept of data science, and we said, if we want to, just give me a second, my apologies, if I can. If we want to say that, yeah, there we go. There is a kind of intersection with deep learning and machine learning. This is how, this is how we can consider data science has a kind of intersection with artificial neural nets, machine learning, and deep learning. And because deep learning is mostly for solving conceptual problems and deals with conceptual data sets, we need to deal with big data. So big data is a subsidiary of data science, and it has some parts in common with deep learning. So this is a very quick review of what we talked in the last lecture. So we said that the thing that John McCarthy predicted never happened, and as a very basic definition of AI was mentioned in page 2, saying that it can be described as the effort to automate intellectual tasks normally performed by humans. And we said that Lady Ada Lovelace believed that we cannot expect anything extraordinary from machines, and they are going to do exactly the same thing that humans normally does. So that is the sentence, that is the quote by Lady Lovelace, saying the analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. And actually, this is the idea behind symbolic AI, as Lucas mentioned. But a person, we talked about that person quite good in the previous session, the name was Alan Turing, said that, well, let's look at this with a grain of salt. Not necessarily we always try to follow instructions to have the answer. Machines can learn by themselves, right? And the gist of all these parts were the mechanism that we had in classical programming, including symbolic AI. We give the data and regulations, and we expect to receive answers. While in machine learning, and for sure deep learning, we provide data and answers, and we expect to have rules. And why we need those rules? To predict the future or to explain the current status that we are in. Although machine learning only started to flourish in the 1990s, it has quickly become the most popular and most successful subfield of AI, a trend driven by availability of faster hardware and larger data sets. I mentioned this, and you remember that was a question that I asked in the class, and I said there were 3 major facts that made us machine learning to be available. One of them was faster hardware or improvement in the hardware. Having the internet that provides larger data sets, you can easily communicate and get the data from different places. And also the algorithms were developed. So these 3 factors shaped the, and you see that here I mentioned it in the lower part of the screen. After that, we said this, that machine learning is based on 3 major factors. The input data, the examples of the expected output, and a way to measure how good an algorithm works. And that is what we could call accuracy in some places, precision. In some places, we measure it by calculating the square error, like in regressions, or absolute errors. And we are going to use that. And guys, from this moment, we are going to touch the concept that you can see in the quiz. So We use that as a kind of feedback signal. Let me just see how many of our friends are already in the my apologies. I can't find. Okay, so we have 65 participants. Okay, so we use that as a kind of measurement, how far from the perfection we are, and then we are gonna correct ourselves. This is a mechanism that we very much use in deep learning. And the difference between what is, let me just show you. Remember, guys, in the previous week, I said what would we call the actual or true labels? Can you please tell me? The ground truth. Yeah, that is but that's a correct answer for saying that loss score and loss function. But what are the actual or true labels? They are Y's, right? And what are the predicted outputs? Excellent, Lucas. Yes, they are Y primes. And the difference between these two, as Lucas mentioned, provides the loss for us, loss score for us. And who is responsible to calculate that? That is nothing but loss function. So loss function is responsible to calculate how far we are from the correct answer. And a machine learning model transforms its input data into meaningful output, a process that is called learning, right? Look at this example. You remember that we said we are going to have some input here, right? Some inputs here. And then we have hidden layers, and we try to get to the output, correct? We said that we call every single of these circles, guys, what do we call them? There are several names. I want you to review all of them. What do we call every single? Okay, for Minat, that is correct if we are dealing with pictures. But what about the more? Yeah, all of the answers are correct. Neurons are good names for them. Nodes, correct, but the most common things that we use for them is neurons, right? And the other that I want you please remember is activation. So neurons, activations, right? And what are these edges that we have here? Lines, okay. Yes, we call them weights. Actually, they are weights, true. And I said we do not see something but we have values that we add on top of each column. So we are gonna have those values that we impose, we add to each column. What are those values, guys? Lucas, parameters are correct, but we call both weights and biases parameters. That's a good thing to consider. Awesome. So parameters are both weights and biases. As Al Gore mentioned correctly, we call them biases. And I told you at the beginning that in the previous session, that the values that initially we have for weights are, can you please just fill in the blank? The initial values of the weights are defined based on what? Yes, randomly. They randomly defined. And in most cases, I double checked. In most cases, biases start from 0 and then they get increased or decreased based on the scenario that we are dealing with. So random weights and 0 biases. And okay, the central problem in machine learning and deep learning is meaningfully transform data. What is the meaning of transformation of the data? Is there anybody who can explain that? Extracting valuable data. Good, Prakash. What else? Simplifying the data. I like that, Parsa. Very concise, very right to the point. To find underlying representation that can be applied to consistently categorize a specific data set. Anand is saying transform the input data, which is one type, for instance, picture, to another type of data, for instance, numbers. Very accurate. Yeah. So Algor said to make its representation more understandable. Carl said visualization. Okay. Well, representation in what we can first think of is what Carl said. We think that it should be relevant to visualization, but here we are talking from the computer's perspective. We have something that computer has no idea about, like a handwritten digit, right? So computer just look at it as some pixels. In a very simplest form, we want to bring that picture of a handwritten digit to something that computer can understand, which is a number, like between 0 to 9. Does that make sense? So representation here means to present the data in hand in a way that we can just label it something meaningful initially for computer. So that is what, guys, are you following this? If you can get this part, this is the most kind of sophisticated part to grab at the beginning. We have a picture that we can understand, but computer cannot guess what that picture means. So we are going to imagine that you cut the picture into some columns and put the first column here, the next column starts right after that, and so on and so forth. So the first thing that we did, we just make it a kind of flat. We call it flattening, right? Or reshaping the data. If the thing that I said means changing 28 by 28 pixel to a column of 784 is clear, please type 1. If you have any concern, please ask. Enes, thank you. Casey. See, why? William. Farsal, Khadija. Okay, bravo. Thank you very much. So now we have something that if there is a pixel over there, we say, guys, I simplified. If there is a pixel which is handwritten digit across that, we say it is, for instance, 1. And if there is no line in that pixel, we say it is 0. And we just bring that those data from this layer to the next, linking them with every and all neurons in the second layer. This is a first hidden layer, actually. And we know that we have weights here, and we impose a bias on top of this. And because it is random, right, then we keep doing this for the next layer and so on and so forth. And guys, let me ask you one thing, and it is very intuitive. There is no trick question here. Because it is random, I repeat it, because it is random, what could be the chance that whatever digit that you provide says it is 0? What about the chance of 1? I'm saying regardless of any handwritten digit, right? At the beginning, computer doesn't understand anything. What do you think that the chance of being 0? I'm sorry, let's paraphrase it. What could be the lovely, you said it. Thank you. I wanted to paraphrase myself. You already answered it. The chance of each of these possibilities, because we have 10 options, it could be 10% for each. Again, I'm telling you, because it is random, right? And when we get to the last part, guys, how can we correct ourselves? Anybody, if you pick a mic and start speaking, that would be amazing. I think that it's going to be a little bit of change and people enjoy your voice too. Anyone wants to pick a mic, please type. Yeah, so I'm asking, Lucas, Ali, I'm asking that. Now, I said 10% is the chance of having 0, 10%, 1, 10%, 2, and all the way to 9. But the actual number was 4. Okay, so how can I proceed and correct this to a better guess for the next round? Can anybody tell? Compare. Okay, compare with. Yes,
I could say something.
please.
Okay. From what I read, basically, you need a feedback mechanism for the model or for this this network to basically guess a second time to try and get closer to the actual value. So what happens if it has a 10% chance initially, it will probably get it wrong. Then the loss function will basically create a loss score, which shows the delta between the correct answer and the answer that this model gave. And then that loss score is then feeds into something that I read called an optimizer, which uses something called back propagation, and it basically forces the network to now readjust, I believe, the weights or the biases, I don't really know, to then have the model try it a second time and hopefully be closer to the actual value of 4. And if that loss score continues to shrink, it should eventually get to the correct answer. I believe that's what it is. Also, actually, before I go, can I just ask you a question? Because I quick clarification. So the weights are the lines between the neurons. Is the bias that's the bias of the entire column, right? That's a single number for the entire column. Is that? Sorry, I just want to make sure I understand that well.
I will elaborate on them. Thanks to ask. Let's just change it a little bit to a kind of accent color. Okay. Do you see those orange arrows?
Yep.
Okay. These are the place that we impose biases. We add biases, and they are just one number for the whole column.
Okay, thank you. And
No.
are the biases random or are the weights randomized?
Okay. Let me just put it this way. We have different mechanisms that they implement that. The most common way for almost every algorithm, they use random numbers for weights. All the algorithms that we have in AI, deep learning, they use random numbers initially for weights. But for biases, mostly close to they use zeros. They add zeros at the beginning and then they shift and they change it based on the backpropagation that you said. Okay. Let me ask, guys, I have intention to ask you several times. Lucas, thank you very much. Thank you very, very much. I'm gonna write your name here. Okay. Anyone else can explain that again to me? And I have intention that. How this works, imagine that, okay, let's change the example. I have 1,000 of the cat's photos and 1,000 of dog's photos. And then I want you to just come up with this idea. What could be the chance of saying, no matter what the photo is, what is the chance of saying it is dog or it is cat? What could be the percentage of the chance? Okay, I expect everyone think about that, and no matter if you answer it correctly or not, but give the answer for it, because it shows that we follow and we grasp, so we can just proceed and build based on that. Again, imagine that a very simple question, and this is what you can just change cat and dog into this question. Imagine that you flip the coin and now you have the coin. What could be the percentage of the chance that you see head or you see tail? What is the percentages? What could be the percentage of seeing head? Lovely. Excellent. You have a picture. We don't know if it is cat or dog, but because it is initially random, right? What could be, so we have just two labels at the end, cat, dog. Okay. My question for you is, what could be the percentage? What could be the percentage of saying that is cat or that is dog? Again, the same thing. Ronnie, thank you. Raul, thank you. Karish, Abhishek, Min, Ali, NS. Yeah. One of the things that I want you to think, and tomorrow you're gonna just consider. This is something funny, but I have intention to ask you that. If I can just click on the. Okay. Okay. Guys, anybody recall what is this? Is a lot more than it being just 50%, because the model will try to pick up features that are unique to cats or dogs. Initially, Ali, I'm talking about the initial stage. At the beginning, because also depends on the training data set. Okay. It's good. I'm not gonna say anything to say, for instance, if I have different opinion, we are gonna proceed and you are going to correct me if still I make not valid. Okay, guys, can you see the screen of my computer? Lovely. Anybody has any idea what is this? Let's just quickly see a few seconds of it.
Great.
Can you hear the
Nice work.
voice
What's in
as
that?
well?
That is a burrito for the test. Good to know. Oh, let him have it. Guilfoyle thought he was too good to work on seafood, and now he's about to lose fortunes.
Okay, ready for test. After you, milady. Oh, this is weird. Mia just asked me good luck with the demo. Then you guys.
Okay. Now, do you know what is this series? I very much like you to search it on Silicon Valley. Lucas, bravo. Yes, very funny. And yeah, that's amazing. Just the thing is, and this gentleman, this gentleman provides a production seafood, but SEE food, right? Kind of thing. And what is the situation that it is going to deal with to check if a product is hot dog or not hot dog, right? And this is the most common, guys. We all laughed at these scenes, but the reality is saying if it is cat or not cat, if it is valid or not valid, is the most common problem statement that we deal with in the world of machine learning and artificial intelligence. Okay, what we are going to do tomorrow, we are going to find some other examples like hot dog or not hot dog in different aspects, and we try to find features for them, just to give you a heads up. And please allow me to continue, and I'm going to talk about the things that one of our friends, if I'm not mistaken, Algar, commented that Ali said that it should be more than 50%. Ali, you are absolutely right, but if we have a kind of critical mind on the other side, which says, okay, let's consider this column is more important and the other one is not important, and so on and so forth, right? But one of the things that we are dealing with in deep learning is, neutrally, we do not distinguish or segregate the columns that we fit our data set with. We say that they have equal weights at the beginning, and the system is going to learn. That is the whole idea. Okay, you remember we talked about those spots, and we said, what if we change the coordination of the x's, and it's going to calculate the new coordination, and said, okay, based on that, those who are on the left side or right side, they are white or black. But the best could be, so in this condition, we first have a kind of transposing the coordination, and then recalculating the position of each spot based on the new coordination. So we have two phases. The easiest could be, the best could be just we transpose all the x's and y's of the spots once, and then it's going to ease the job. Those who are less than 0, the x is less than 0, they are whites, and those who are greater than zeros are black. And you see that exactly because of this, we could have different representation of the data, and those that are important for one problem statement are those that we are gonna pick. We said it could be possible that, if I can just see that RGB, and it was somehow around here. We talked about, yes, it is here. We talked about that it really depends on the problem. If you are searching, for instance, for the color in one picture, the best mechanism to choose the best representation could be based on RGB. While if you are searching for saturation of the color, HSV could be a better representation. So it really depends on the problem statement. And after that, we said in machine learning, the problem is we have limited number of options for each algorithm, and we limit ourselves to hypothesis spaces. I told you an example. Anybody recall? And it was about Canadian Tire. Okay, can you please paraphrase it the way that you want to explain? And I see a hand raised. Sorry, if there is any question, please ask. Oh, it's my hand raised, really? Okay. Okay, I have a question about hypothesis space. Are these just the predefined set of operations? Exactly. The steps are limited and predefined. And that is why that some data sets work better with some algorithms, and they could get worst results in the others, right? We do not have that much room for maneuver. Absolutely. Okay, Ali, whenever you just mentioned it, I mentioned I'm gonna continue what Lucas said, that so someone made these already, and so we have those algorithms, and we are gonna just use them. Someone has made tools for us. We go to one specific aisle and pick, for instance, a plier or a screwdriver, because the problem that we have is, for instance, just fixing one specific screw to just get the job done. And no novel new algorithms. Yes, there is no novelty. We just use the tools that we have there. But in deep learning, actually, it's like making your own instrument, making your own tool, right? And the thing that we have here is based on successive layers. And compared to have several hidden layers, we could say the normal machine learnings can be considered as shallow learning algorithms because they have one, maximum 2 layers. Okay. And I don't know how I can fix this. Okay. So based on that, we said every single of these layers, because we have several layers, could consider as a sieve or filter that purifies the data towards the final output that we're expecting. Again, what we have is a picture that computer has no sense, no feeling about it. And we want computer to consider this is number 4. So again, getting back to this this picture, at the beginning, we are going to just have some random weights, 0 biases, and then the number is whatever it is. It's going to say 10% is the chance of 0, 10% because it could be like 9%, 11 or something, but they're in the same range. And after that, this is the most important thing, guys. This is what I asked you. We have what we predicted, which is y prime, and we have the actual label, which is y. The difference between these two is the loss, is how far we are from the perfect answer. Does that make sense, guys? If you get that, please type 1. Let's simplify it. Exactly. Guys, look at this one, please. No matter what algorithm we are using, machine learning or deep learning, this is common between all of them. We have some samples, right? And in front of each sample, we have a label. Does that make sense? So for instance, we have lots of pixels that this one is going to represent number 4. We have another row of pixels, those 784, which says it is number 7, and so on and so forth, right? Imagine for the one which you predicted, for the one which is actually number 4, you predict it is 8 or something. So you are not in a correct position. So then the weights and biases are not correctly set. Does that make sense? So we have something that we predicted, which is y prime, while the actual label is y. Do you get that? Those people who didn't type 1 before, look, I predicted it is number 7, while the actual number is 4. So they are not the same. The label and my prediction are not the same. Something is missing. Let's calculate that distance. Let's calculate how far we are from the perfection. This is the responsibility of loss function to calculate that, and the result would be something that we call it loss score. If you get that, especially I'm talking about those friends that they didn't press 1, can you please type 2 if you understand this one? Okay, awesome. Look at this one, and please read these pages before you start answering the quiz. Look at this one. The loss function, which also known as objective function or cost function, is responsible to calculate these differences, right? And because I calculated for the very first time, I'm talking about the very, very first time, I started going from this side all the way to this side. It was like a forward process. I calculate the loss score thanks to having loss function or objective function, my apologies, or cost function. They are all the same concepts. They're all the same. We need to fix weight. This is a kind of tiny, teeny problem of the book. We need to fix weights and biases. In the older version, it just had an arrow to these weights. Now in the recent version, they fix it by having the arrow to those, but it needs something more as well, and that is fixing biases. So loss function is going to be fed sorry, it's going to fit the optimizer to change the weights and biases. Look at this one. The fundamental trick in deep learning is to use this score as a feedback signal to adjust the value of the weights a little in a direction that will lower the loss score for the current example. I don't want to give any answer at the moment, but I just want you to think about it. Do you think if you have 1,000 pictures, most of the time we have tens of thousands of samples? Do you think that it is rational that I start calculating the loss function for every single picture? Ali said, so basically it is learning from its mistakes. That's exactly like our life. Exactly, Ali. Yes. I repeat my question. Yeah, Anand, it was not easy to get to that stage. If you read this, the history of it, you're gonna love it. It was a kind of, as it was mentioned in the book, it is nothing short of a revolution in the data. Okay, guys, did you get that? We have random weights and biases. We predict y prime. It would be awful at the beginning, but the good thing is we have a cheat sheet. We compare y prime, our initial prediction, and y, and then the distance between them. So we have a loss function to calculate how far from perfection we are, right? And then optimizer is kind enough to tweak, to change, to alter the weights and biases to make it a little bit better. My question was, imagine that you have 10,000 photos. Do you think it is rational that I calculate the loss score for the first one, do all the optimization, then go to the next, and do it 10,000 times? Do you think it is possible for sure? I know that I'm not going to waste your time, but do you think that it is efficient, as Anand said? Okay, let me just give you, lovely. Thank you, Anand, Ali, Lucas. Let me give you another possibility. How about this? We have 10,000 photos. Don't do anything. Let's calculate the loss for the first, second, third, all the way to the end. 10,000s. After 10,000s, then we say, okay, you know what? The average of loss for 10,000 was like this amount, and let's go and tweak it a little bit. Do you think this side of extreme would be good or no? Ali said, not really. Sounds better, but not. Lucas said because the wildly efficient loss score, the average would not be a useful measure. Is there any trade-off? Is there? I could just simply read and tell you the answer, but I want you to find the answer yourself. That's why I invite everybody to participate in this discussion. And look at this one. And because of the time, and I need to go to the other class, I summarize it, pinpointing the important things in the quiz. Look at this one. The weights are, the networks are random values that we initially assign. And that is why we could have not correct answers at the beginning. And we train our model for, I don't know, 10 times, 20 times, 30 times, and that is what we call it epochs, so every round that we have. And the thing is, let's do it something, Enes said, looks like more accuracy, but will be slower. That's not very much, because the widely score, the average would not be a useful measure. How about this? Let's pick 100 out of 10,000. Just calculate the loss score for them, average loss score for 100, then ask optimizer to change the weights and biases. Guys, what about that idea? I repeat it, not changing after every single, not waiting till 10,000 pictures. Let's just see 100 and calculate the average of loss score and then tweak optimizer for that. Right? So this is the kind of trade-off. This is what we call it batch size. So if you're gonna see in the hands-on practice, that is the, what do we call it? Just give me a second, my apologies. I want to make sure that I leave you with enough knowledge to start your quiz. Just give me a second. So this is a journey that we are going to continue tomorrow. Focusing on the, I'm telling you, we don't have that much. It's just knowing the concept. So let me ask you one thing, guys, and please, everybody, answer this. The specification of what a layer does to its input is stored in which part? What we do in every input neurons. What is the thing that changes that neuron's value and pass it to the next layer? I read the question. The specification of what a layer does to its input data is stored in the okay, just exactly we have that in the book. Please, before getting to the questions, check the book, read the book quickly. I'm not telling you where you can find that, but the specification of what a layer does to its input data is stored in somewhere. I don't know where. Okay. And the next question is, I just want to at the beginning of the session, I said, yes, Lucas, thank you. We call both biases and something else as the parameters of a layer. What are those things that we call them parameters of a layer? Yes, thank you very much, Lucas. And the last question that I have for you is, okay, how about that? Let's just keep the challenge. Guys, read these parts, especially after page 5, and more emphasize on page 9, 10, all the way to before this this part. Okay, please read them before starting the quiz to get the best result out of it. Thank you very much. I wish I could stay more. I know that some of you might have questions. I would be grateful if you bring your question to tomorrow's session, and I'm gonna go and start my Python class. Again, once again, have a wonderful one. Thanks for coming and take care of yourself. Ciao. Bye.